Today we're going to talk about how the derivative is related to the graph of a function. And so let's first just go over some vocabulary, and we'll do that visually. So I have the graph of a function, and I want to know where is f increasing. A function is increasing if, as you read the graph from left to right, it's going up. I've shaded those regions in red. In this particular case, we could describe those regions as everywhere from x equals 0 to x equal about a half, everywhere from x equal 2 to 3, and from x equal 4 to 6. A function is decreasing if, as you read it from left to right, the graph is going down. In this case, that would be x equal a half to x equal 2, and then x equals 6 to x equal 8. Finally, a graph is constant if it's horizontal, so that would be from 3 to 4. Now, local extrema are basically high points and low points on the graph. I've indicated them in red. This particular graph has 2 local high points, 2 local maxes, and 1 local min. They are located at x equal a half, 2, and 6. Now, this information about increasing, decreasing, constant, and local extrema can all actually come from the derivative of this function. If we remember that derivative is slope of the tangent line, that means if the derivative is positive, the function has to be increasing. Positive slope, increasing. If we have a negative slope, or the derivative is negative, the function would be decreasing. Intervals where the derivative is 0 indicate that the function is constant. The second thing I want to point out right now is those local mins and maxes occurred at places where the function transitioned from increasing to decreasing and vice versa. Those are also places where if I drew a tangent line, I would have a horizontal tangent line. So this screen right here basically summarizes the details that I tried to show you in the previous example. That if the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. Now, one piece of vocabulary, that word critical numbers, is going to refer to places where the derivative equals 0 or where the derivative doesn't exist. The idea is a critical number is a place where a function could change from increasing to decreasing. And in order for a function to change from increasing to decreasing, it has to either have a horizontal tangent line, or it could have a sharp point, a place where the derivative doesn't exist. So critical numbers are places where functions can change from increasing to decreasing. Critical numbers or critical points are also places where maximums and minimums can occur. Now, not all critical points are maxes and mins. We'll have to do a little bit of work to determine if we have a max or a min. And the work that we're going to do is summarized in the next statement, which is known as the first derivative test. The idea is we have a max if the derivative changes from positive to negative, because that means the function is increasing, then decreasing. We have a min if the function is changing from decreasing to increasing, or if the derivative is changing from negative to positive. Now, there's a lot of information on this screen, and I think it's going to be easiest for me to explain this to you through an example. So let's just dive right in and try to look at all of these things through an example. For the function y equals 4x to the third minus 9x squared minus 30x plus 6, let's find all critical numbers first. Critical numbers are places where the derivative equals 0 or where the derivative doesn't exist. So I'm going to start by finding the derivative, which is 12x squared minus 18x minus 30. And then I'm going to take that derivative and set it equal to 0. I'm going to solve this by factoring, and it looks like we've got a common factor of 6. So I'll pull out the 6 first. I'm going to continue factoring, so I need two numbers with a product of -10, a sum of -3, -5 and +2 work. So copy down the 2x squared. I need a -5x plus 2x. Copy down the -5. First two, I pull out an x. Second two, I'm going to take out a 1. And so in factored form, this is 6, 2x minus 5, x plus 1. Now I set all my factors to equal to 0. The 6 can't equal 0, though, so that doesn't give me a critical number. But if 2x minus 5 equals 0, I get x equal 5 halves. And if x plus 1 equals 0, I get x equal -1. So my critical numbers are 5 halves and -1. Now we're going to answer parts B, C, and D at the same time. Based on our information, our critical numbers, we're going to try to figure out where is the function increasing, where is it decreasing, and does it have any local extrema. And so what I'm going to do is I'm going to make a table, and I'm going to use the number line to help me. And I'm going to put my critical numbers on this number line. Then I'm going to analyze where is that derivative positive and where is that derivative negative. And so I'm going to pick a test value in each interval. So I pick something that's smaller than -1, something between -1 and 5 halves, and something that is larger than 5 halves. And then I'm going to take these test values and I'm going to plug them into my derivative. I think I'm going to plug them into this factored form of the derivative, but it doesn't actually matter. You can plug it into any of your variations of your derivative. If I plug -2 into that derivative, I end up with a 6 times a -9 times a -1. The important thing to notice is we are going to get a positive solution there. Two negatives give us a positive. Now I'm going to plug 0 into my derivative. 6 times -5 times 1 is -30. The important thing is I got a negative solution. My derivative is negative. And finally, if I plug x equal 3 into that derivative, 6 times 1 times 4 is 24, but the important thing I'm looking for is that is a positive number. And so this table tells me that the function is increasing when the derivative is positive. So in interval notation, that would be everything from -infinity to -1, and then everything from 5 halves to infinity. This function is decreasing when the derivative is negative, so that's from -1 to 5 halves. And then as far as the local extrema, this function is changing from increasing to decreasing at x equal -1. So that's going to be a maximum. And it's changing from decreasing to increasing at 5 halves. That's going to be our min. Now, when you find your max and mins, I do want you to give your answers as ordered pairs. These are points on the graph. And so to finish, you're going to take the x values that you found, and you're actually going to plug those into the original function. Okay, so I'm plugging those x values into the original function, the starting function in the problem. I used a calculator to help me with this. When x is -1, I got a y value of 23, and when x was 5 halves, I got a y value of -62 3/4. So those are the coordinates of my min and my max.